Hello everyone, welcome to our Egyptian online seminar group. First, keep your microphones off. Then, if you have any questions, we can ask our speaker during his presentation or after his presentation. I have great pleasure of welcoming Professor Miguel. Miguel is a department chair and associate professor of accounting at the University of Miami, Herbert Business School. He was senior economic research fellow at the PCAOB. Miguel research interested are in capital markets, particularly in auditing, financial reporting, and the methodology issues. He is working on various projects related to expanded auditor report, auditor communications with audit committee, auditors use of specialists in complex area production models using machine learning and other topics. Miguel is editor of Contemporary Accounting Research, associate editor of Journal of Accounting Research, and member of the editorial board of Review of Accounting Studies and the Auditing Journal of Practice and Theory. He has published articles in this and other journals. In 2020, the auditing sections of the American Accounting Association gave the notable contribution to the Auditing Literature Award. To one of his early papers, co-authored with Lawrence and Zhang, Miguel received his Ph.D. In accounting and the Master of Management Professional Accounting from the University of Toronto. Now we will start our seminar with Professor Miguel.
Thanks, Mohammed. Thanks for putting together this venue for researchers across the world to present and discuss ideas, and very importantly, are interesting, sort of like an independent voice in this type of setting, right? That's actually very unique. I have the pleasure of today talking about this paper that has evolved since we presented something similar at the FARS technical session this spring, and has become a more evolved, a longer paper than whatever is available online. So a lot of the things that I will discuss today are not yet in the, so they're going to be like first timers. They're not yet in the version posted on SSRM, but it will be soon revised, and hopefully we will see this paper in a journal soon. The paper is called Regression and Machine Learning Methods to Predict Discrete Outcomes in Accounting Research. It's a highly technical title, I think, but it's a highly technical issue. And it's co-authored with my good friend and former student, Jay Krupa, who is at Tulane University. The motivation and objectives of these papers start with a renewed interest in prediction modeling in accounting research. There's always been prediction modeling. There is a number of papers that rely on prediction modeling, but with the advances in machine learning and artificial intelligence, we've seen way many more papers that rely on prediction or that explore the prediction of certain variable that we used to see before. So, and our goals are, first, provide practical guidance, including mainstream techniques, discuss some unique problems that accounting researchers face, and explain the tools to assess out-of-sample model accuracy, economic significance, and go beyond model building. So our assessment of the literature, both in accounting and somewhat out of accounting, just to put it out there, neither my co-author or I are experts on machine learning per se. Like, we don't come from the machine learning stream or from AIS stream. However, we've been interested in these type of models for a long time. Prior to this, we had a paper on predicting bankruptcy using going concern opinions. And we found that when we're trying to learn more about these models, and we try to go deeper on how to estimate it, etc., we found a general lack of accessible guidance, and we found a lack of a paper that could bridge the gap between statistics, machine learning, prediction literature, and the accounting literature. And as such, we took the opportunity given by FARS and Journal of Financial Reporting to propose this topic. And then we've been lucky enough to have a paper on this area. Now, the first thing I want to highlight is that prediction modeling is mainstream accounting literature. For some people, it might sound like, well, this is a niche topic, or this is some more of a systems topic, or data science. But in reality, we have papers that predict outcomes or aim to predict outcomes since long time ago. By far the most common literature is in fraud, right? So there is the very famous, very cited, the Cairo paper trying to predict AERs in car. Then there is a follow-up paper by Sekini et al. In management science. And there are other papers by Perols et al. In Account Review, AJPT, and there is recently Bao et al. In JAR, right? So all those papers are on the same topic, and they are all in very top journals. Then we have a bankruptcy that in the 70s, 80s, and sometime recently, they have received the attention of accountants, but we by no means claim ownership of the bankruptcy literature. The bankruptcy literature spans economics, finance, accounting, and also machine learning and data science. Then there are recent papers on restatements, some papers on going concern opinions, litigation, internal control weaknesses, auditor switches, and then we started to see papers on accruals, impairments, predicting the direction of earnings changes, like the famous Penman paper that keeps coming back now in machine learning. So we feel that the list of papers on this trying to predict some important outcome is very large and is very high regarded. So we feel that this is something that motivates us to keep doing more of these. Now, our takeaways of this literature is that there is a new wave of machine learning applications. So there is a lot of papers of let's redo what we know, but now use some machine learning model, right? And that is particular, for example, in this stream of papers, a lot of them, most of them are in working paper format, trying to predict the direction of earnings changes. And there are also, there is also a paper on Rust trying to predict bankruptcy using boosting, that is just a remake of the bankruptcy literature. And we also feel that there is high startup cost, but the advantage is that now widely available statistical packages allow to do data management, processing, creation of variables, and estimation of these models in the same package, right? And I think the tools are the stage in which, if you know how to use data in particular, you can do everything in the same package without having to know Python to do certain tasks, and R to do other tasks, and SAS to do other tasks, right? Now, in general, there is still high concerns about data mining, but the opportunity to perform theory testing and improve existing models is open, right? I think at least some people are changing their mind about the value of these exercises that appear as data mining, right? And there is also a mix of computer, data science, and statistics, but this is not widely taught in econometrics or other PhD courses, right? So the way the knowledge has evolved is, or continues to be, is we go to our PhDs and then we get taught traditional econometrics, and then we get taught statistical models. But there's really not a lot that we learn about these tools from data science, right? Although a lot of schools now offer courses in machine learning, like our own PhD students here in Miami take machine learning courses, but they are somewhat disjoint from their education, right? So we feel that at least there is a need for a one-stop paper that will bring a lot of the basic foundation knowledge for our research community. And also we feel that these type of papers they not only have academic impact, but they can have practical applications, right? So there is a lot of people out there, regulators, practitioners, investors that are interested in predicting the probability of something, right? So for example, the idea of predicting the earnings changes and then trading on the predicted direction of earnings tradings, right? Of earnings changes. That has been a subject of interest to accountants for a long time. And it's also a subject of interest to investors, right? Now, this is a paper that we found somewhat complex to write because we need to give a literature review. Then we need to give an overview of the most common tools. And then we need to give steps of how to perform the prediction process. So in my talk, I'm going to follow a little bit of a different outline as a paper. So first, I'm going to go over the steps required to do or recommended by us to do the prediction modeling. And while I go through the steps, I'm going to also introduce the models that we're going to discuss in the paper, and then at the end we'll deal with an example. So the first step, and this is sometimes I feel taken for granted, is to understand the outcomes to be predicted. I think that before going to any data, before going to any variables, it's important to understand what is it that we're predicting. In our case, although we could have taken the choice of discussing models for continuous variables, discussing models for 1-0 variables, and the frontier between these two is actually blurring. We're going to limit our paper to 1-0 variables because we have to count somewhere. Now, once you are going to predict a 1-0 variable, it's important to think, what is the frequency and what is the separation between the zeros and the 1? How different are they? How are they defined? And how they occur, right? And this is unique because we're going to have some outcomes like bankruptcy that only occur 2% of the time. And then they occur only within the subsample, typically of the subsample of firms that have negative returns, losses, and negative cash flow from operations, right? So it's a very infrequent variable that only occurs in certain part of the space more often. Then we have fraud versus not fraud, right? Fraud is even rare. Fraud is a 1% occurrence. And then we know that it's related to accruals, growth, market pressures, and that there is sort of like a build-up towards fraud. And also another problem is that fraud is not necessarily a discrete outcome, right? It's not necessarily that there is fraud or no fraud. We have fraud years and we have non-fraud years. And very often fraud years are bunched. And then at the early stages of fraud, it's very difficult to detect. Even what the AERs by the SEC call fraud, they're not something that is very clear-cut, right? So sometimes the period right before the AER identified by the SEC is also a fraud period, but they cannot deem it fraud because they cannot find proof. And then there is restatement versus not restatements. For example, this variable occurs 10% of the time, and is more often occurring for companies with fair values, leases, revenue recognition issues. And the issue with restatements is that the same company could also have multiple restatement years, right? Or restatement periods, right? So you restate 2007, then you have 2 years clean, then you come back for a second restatement, and so on. And then we have restatements that occur over quarters. We have restatements that occur over full fiscal years. And then the next thing is, well, and overall is not giving for granted the nature of 1s and 0s. And then the next thing is how well understood by the world, and not only by researchers, but by a wide community, is the assignment process that generates the outcome. And I think this is where we often fail. And after having done a lot of research on propensity score matching and how do you estimate propensity score matching, I sort of feel that there is a long discussion about you should have included this variable, you should have not included this variable, instead of just coming up with, well, there are certain variables that really define the outcomes. And these are the variables that matter, right? So it's important to sort of really get into how well does the world understand a process. And also a very important thing is that we need to separate the true mechanism that creates ones and zeros versus the mechanism that a researcher can sort of elicit through machine learning or through some other regression techniques, right? So there is a real model, and there is a model that we're going to approximate, right? And very important, yes.
Devin, have a question? You can
Yeah, Miguel, is this a good time for a quick question?
Oh yeah, go ahead. I was thinking, so I can go on and on and on. I only have 30 slides. Go ahead.
Perfect. So my question is about type 2 errors, right?
Yeah.
So you talked about how fraud is so rare.
Yeah.
But we don't know that that's the case, right? The found and disclosed fraud is rare. Yeah. But you've got some of these prediction papers that say, 15% of companies are actually committing fraud a year, but there's absolutely no way to know that. So how can we rely on a model where the type 2 error rate is never really known?
Yeah. There are different ways to see these. One way is to say, well, discoverable fraud, right? And that's what we're actually modeling. That goes back to this part of the talk and this part of the paper, where it says we need to understand the outcomes to be predicted. When we train a model, either Logit or machine learning, to predict AAERs, we're not training a model to predict fraud. We're training a model to predict fraud as discoverable by the SEC. And this is something very, very important for people to understand, right? That if the model is trained to detect AARs, the parameters created by such a model are going to serve to detect AARs, not to detect real fraud. And that's something we can't go further than that, right? Unless we have a way to train our thoughts in the form of these prediction models using observable data, there is no way to attack the problem, right? So we are limited by the observability of something, right? But then perhaps we need to find different ways. If we wanted to really attack the question that you say, there is a lot of fraud that goes undetected, then we would really need to know how does an undetected fraud look like, right? Which I really don't know. I don't know if I've answered the question, but I think it's a little bit of a non-answer. But the question is also the question is beyond the frame of the prediction models.
Yeah, no, that's exactly what I was looking for, just to make sure we distinguish between we're trying to predict discoverable versus the undiscoverable might look very different and might not behave similarly in that model. So yeah, your answer was the distinction I was going for.
Yeah, I've actually this is a perfect timing. We're about to send the paper back to a journal that has this journal doesn't have accounting on the name. We're gonna send the paper back to a journal that doesn't have accounting on the name, and that'll be a good remark. Thanks. Yeah, that's the limitation of prediction models is that you need to learn on real outcomes, right? Thanks. So, and then this goes a little bit also into the second part. I don't think we understand very well why companies commit fraud. And we don't understand very well yet how the SEC comes across and identifies companies that commit fraud, right? And in our replication or our illustration, I'm going to show you that we don't understand very well how the SEC chooses companies to investigate, right? So I think that's something that we need to probably do more research about. And there is some behavioral explanations. There are some economic explanations for fraud, but we need to do more about And then after you sort of narrow down to a problem that is observable, that is measurable, and that can be defined in sort of very narrow occurs, not occur labels, then we need to find some variables that are observable, that are defined, and that can be used to predict that outcome, right? So in that, there is going to be two choices. First, we need to do a model selection, and then we need to do a variable selection. First, I'm going to talk quickly about the predicting variables. How do you select predicting variables? Ideally, from everywhere, right? So you're going to use theory, you're going to use experience, and you're also going to rely perhaps on machine learning to come up with an extended group of variables, right? So here, luckily, the new techniques allow us to err on the side of caution, and we can include hundreds of variables, thousands, right? But here, what we need to think about is not just which variables will go in the model, but also how the data comes to us that will convert into variables. And if you look at practitioner applications of machine learning, this is where most of the time goes in, right? Figuring out what to do with missing variables, with zeros, with outliers, standardization. Sometimes it's called data regularization. But most of us in accounting sort of often don't care about these. We just take CompuStat, CRISP, maybe do winsorization, which is not very recommendable, as one of my papers shows, or it doesn't do anything. So there is also some thinking that will go into that. And then after you have a set of variables that predict outcomes, and by nature, these variables need to precede outcomes and be able to be observable, at least by you, before the outcomes occur, right? A big problem between prediction and association tests that we do in accounting is that ideally, for a realistic prediction model, we need variables that are observable before the outcome, right? Or independently of the outcome. And then once you have some outcome variable, some predictor variables, or at least a wide set of predictor variables where we suspect that we can find predictive power, then we're going to move to a family of models. Is this a big deal? Actually,
Miguel?
Yes.
Can I ask you a quick question?
Yeah,
so,
go ahead.
How do you think about fixed effect? What would traditionally be fixed effects in other models? So it seems problematic to put in either year or observation level indicators. It's not something I've seen in the machine learning literature that much, but it seems like something that us in corporate finance and accounting don't really think about at all. We just put them in. But if you're in a prediction problem, it's not just like, that next year is going to be 2022, but there's no sense of what is the average level of fraud going to be in 2022, which is what a fixed effect would represent, much less all of the nonlinearity that would come in even a one-layer neural network, or let's say a two-layer neural network.
Yes. So that's actually something that we haven't discussed much, but I will add something about that. That's actually an interesting issue. I will see fixed effects of two kinds. One fixed effect is more related to your inherent type, right? For example, in a very broad social science research, male versus female, right? That's a fixed effect. That's an indicator variable, but it's also a fixed effect, right? And a bunch of processes in life are different male versus female, or a bunch of effects in life are different according to your age group, right? So let's suppose you have
fixed effects are a subclass of categorical variables.
Exactly. Exactly. So I think it's important to understand that categorical variables, I do feel they have a lot of prediction power, right? And the most used, at least in historical research, is the industry fixed effects, right? Industry fixed effects have been shown to predict fraud, to predict litigation, and to predict certain things related to the business cycle, right? Now, other fixed effects like for example, company level fixed effects, a company level indicator, let's say, or time fixed effects are something that machine learning people will not think about, right? Because a big gap, and we discussed that in the paper, but it's very important to bring to the front, is that most machine learning applications are not planned based on a panel data set. They are planned mostly looking at something that looks like a cross-section in our sort of accounting lingo, right? This is where your question is very important, because people need to understand that to predict something comes from identifying variation between subjects that will predict the outcome between subjects, right? Now, variation within subjects is not as well understood, right? And this is where some models, for example, in the logistic regression, they have a way to become sort of timed to something, right? And that's where we observe a lot of these survivor models, in which actually the bankruptcy literature moved from logit to survivor models, in which we're not really predicting whether you're going to go bankrupt or not. Is you're going to be predicting your process to go bankrupt, right? And that's where time may matter. And the transition from a pure cross-section to a panel is something that the machine learning literature doesn't really deal with, but accountants have to deal with. So we need to find workarounds, and we discussed several of them. For example, maybe you want to think of a model that you use 5 years to predict what happens in the 6th year. Or maybe we want to do things like think our cross-validation approaches based on this process. But the question is very well taken. It's something that accountants need to think about. And I'll make a comment on the paper about the fixed effect issue and how fixed effects can be seen as categorical or can be seen as panel variables. I don't think seen as panel variables is going to be useful for prediction. Like the year fixed effects, right? Because we cannot say that adding let's suppose you use 5 years to predict the 6th, adding an indicator for years 1, 2, 3, 4, 5 is going to help anything to predict what's going to happen in the 6th. Yeah, that's thanks, Henry. That's pretty useful. Now, another thing that we need to break the mold from a traditional accounting research to the space of machine learning is getting a little bit out of the mindset of t-statistics or within sample fit, like R-square or AIC or BIC, that we don't use a lot in accounting, but R-square and pseudo R-square are very widely used. Because sometimes, and I've seen this in old research based on, for example, whether having a Big Four auditor increases your probability of getting a going concern opinion. A lot of that research just looks at the t-statistic of Big Four. They really don't look at whether the model with and without Big Four is a different, it has higher prediction accuracy. So you cannot really do that kind of test in sample because of all sorts of issues. There is overfitting problems, there is lack of out-of-sample validation. But then on the other side, they're a quick and dirty way to figure out whether this is a process that is well understood or not very well understood. And these are the most obvious extension to regression approaches, right? So the first move from association test to prediction modeling is move from the coefficient to the R-square. But then think that the R-square in sample is just a start. And a paper that did that was the Dichao et al. This should be 2011. This is a paper in CAR that predicts fraud. And they select variables that produce a model with a high in-sample R-square. Now, the new mindset is moving from in-sample R-square to out-of-sample accuracy, right? And to do that, we need to think of the data as there is always going to be a subsection of the data where I'm going to find a model and another section of the data where I'm going to test the accuracy of the model. And this is where a lot of improvements in computational statistics and data science have taken us. Now we don't need to think of sort of two unique samples where we do these things separately. Now, through the use of cross-validation, it can be the exact same sample, right? And then with the idea of cross-validation, which means I'm going to select, let's say, 10% of the data to be the place where I test the model that I estimate of the other 90%, and then I can find another 10%, another 10%, and the tools of accuracy metrics like the ROC or the PRC, the classification accuracy, then I can get a pretty good idea of how good a model is. Now, towards the end of my talk, I want to talk about the idea of a lockbox sample. And here's something where we got some interesting comments from one of our reviewers about even when you do these K-fold cross-validation, it will still be useful to keep one part of the data untouched until the very, very end of your paper, right? So there is different criteria about this, but I think that's actually a pretty good idea, right? So you select part of your sample that you will never touch. Let's call it the lockbox. And then the remainder of your sample, you can use cross-validation to find the best possible model. And so, and you have to do this even before you touch the data to do any estimation. I think that's really, really important, right? Before estimating anything, even a logistic regression, you have to understand how your data comes through, right? So you have fraud or restatements, and then you have to understand how many years of the data you have and whether you're going to randomly select part of it to be a lockbox, and how are you going to do your validation process, right? So how are you going to split the working sample, let's say, between some testing group and some estimation group? And next, you face the problem that I think most people jump to, that is, which family of models should I use? And I think for us accountants, this should be almost a no-brainer. In the vast majority of applications, we should do regression first. We should do logistic regression or a probit regression or a discrete time hazard. The difference between logistic and probit is just very minor. I mean, that's no longer a big issue. But the difference between logistic and a time hazard model is that you may be interested in modeling whether something occurs or not, or whether something occurs after an accumulation of conditions, right? For example, bankruptcy is one of those, right? It takes several years of negative returns. It takes several years of losses, several years of negative cash flows to lead to fraud. But mathematically, these models are pretty similar in most cases. Now, what are the benefits of regression? Everybody understands regression. They are available in all statistical packages. It's really simple to show people coefficients, significance tests, and they can be used in combination with either backward or forward looking and rich or lasso regression to help you in variable selection, right? So they give you a contained space in which you say, these are the variables that are going in the model. These are their coefficients. And you can also use additional techniques together with regression to narrow down your variables to a set that you find is good enough for your problem, right? And this is what accountants have done a lot. But what we have not done a lot yet, and in the new version of the paper we'll talk about that, is using rich or lasso regression instead of forward or backward looking. And what is forward or backward looking? Well, that's a simple process. You start with 20 variables, you add one at a time, or you subtract one at a time until you feel that you found a combo that is highly predictive, right? Now, regression performs actually very well, especially if there is a well-known relation and there are very powerful predictors. And some example that I worked a lot is predicting a Big Four auditor, right? Whether a company will have a Big Four auditor, it's a problem that we can predict with a 93, 94% accuracy, right? And one variable gives you all the size of the client, right? In that case, adding nonlinearities, other terms, other variables are very unlikely to result in a nicer or a more accurate prediction model. Now, what are the costs? That there is a highly important limitation in terms of the number of variables. Only so many variables can go in a logistic model. And functional form matters a lot. Multicollinearity, outliers, missing data, non-linearities are not going to help, right? Unless you explicitly model them. And there is only so many interactions that you can include in logistic, right? And importantly, and sort of thinking of in a different way, logistic regression doesn't consider pockets or regions where prediction changes, right? And accounts have dealt with these in very many ways. For example, in the prediction of going concern opinions, the most common solution is only estimate going concern opinions among loss firms, right? And we draw from the sample non-loss firms or positive cash flow firms. And this is a standard issue in the going concern literature since Hopwood et al. 1994. Does it work? Yes, but is this really optimal? No, but that's how we go, right? Then the next approach, or the next several approaches, and what has concerned a lot of the current literature, is moving to machine learning models that allow for functional forms that rely on a machine-based search to find decision rules to classified outcomes. So here is sort of like interesting. Instead of focusing uniquely on weights, and we can see the logistic regression as a weighted choice, right? So every one of the coefficients is a weight, and if the coefficient is statistically significant and larger, it means that there is a larger weight on that variable in determining an outcome, right? Instead of thinking of that, now we're going to think of a decision rule, right? So we're going to think of prediction more in terms of a classification problem, right? And this is more, some people that work on machine learning say that this is more like the human brain, right? If you're presented with a series of objects and we need to classify them in 2 or 3 or whatever buckets, we're not going to run a regression in our heads. We're going to look at attributes, and we're probably going to start separating and creating groups and subgroups and subgroups that will help us to do these. And a lot of the machine learning approaches have that in mind, right? Some are more mathematical. All of them are mathematical, but then some of them are more based on mathematical functions, that others that are based more on a sort of what will be seen more as heuristic. And where do you start is almost infinite, right? Not almost infinite, but there is a lot of approaches. There are a lot of papers written in accounting, out of accounting. There is an evolution of these techniques, but we find that 4 of them, well, 3 types, but then 4 models are the ones that emerge as very straightforward possibilities vis-a-vis logistic regression. The first are classification tree methods. And from these, there are 2, random forest and gradient boosting. Then there is supporting vector machines that works actually a lot like regression. And then there is neural networks that has experienced a revival on the term deep learning. So in the paper, we're going to focus on these 4 choices. I think if you were in the business of predicting outcomes, it will be hard to say that these 4 choices plus logistic will give you an unreasonable solution, right? So this is how we start. And also, importantly, all of these techniques can be done in Stata today using algorithms that are fairly stable. We've run them, we test them, we try to crash them, and even running on a PC with a reasonable amount of memory, they work well, right? That's what we were looking for, right? So we weren't trying to give people some very niche, cutting edge solution that couldn't be done, right? We want to give you things that were more sort of seamlessly integrated. So there's a question from David F.
Yes, please open your mic here.
Yes.
David, yes.
Yes. Okay, Miguel. Hi. I wanna ask a question. You said machine learning is like machine-based search. So this is more like advanced statistic approach.
This is interesting. Where does machine learning reside is an unknown. Is machine learning a statistical approach? Depends. If you ask statisticians, they will tell you not necessarily, because it doesn't rely on parameters per se, and it doesn't rely on hypothesis testing. And that is the biggest, I think, after reading a lot of these, that is the biggest sort of abyss between regression and machine learning. Machine learning is really not concerned about hypothesis testing.
How about the non-parametric method?
Well, non-parametric methods in statistics are just flexible functional forms, but ultimately they're interested in hypothesis testing, right? Like if you do, let's say, a GAM, where you have a nonlinear regression, where one of the parameters estimates a curve and the others are linear, like partial linear models, you can still estimate around the curve some confidence intervals, right? So prediction model is really not interested in confidence intervals until a very, very end. The only benchmark for prediction is how accurate is this prediction? What percentage of an out of sample sample you can get right? That's all that matters.
But
Right?
here you are looking at the decision rule. So this decision rule is more like trial and error. So the machine is looking at the pattern.
Yeah.
So the machine itself decided maybe which one is the best way to explain it.
Yeah.
I mean, it's different from artificial intelligence.
The difference now, this is interesting. There is differences between statistics and machine learning. The biggest, in my opinion, and others, the biggest wedge between these two is hypothesis testing. Now, there is a lot of hypotheses that will be improved by machine learning, right? Just because we can get better predictors, we can narrow down samples, we can enhance causal inference, right? Now, there is a wedge between machine learning and artificial intelligence. What is a wedge? The wedge is how structured the problem is. In artificial intelligence, and particularly that's where neural networks is moving to, both the dependent variable and the independent variables are up to a computer. So in artificial intelligence kind of things, even the data gathering algorithms, if you think about the sort of the most, probably one of the most common issues now under debate is the Facebook algorithms, right? So the Facebook algorithms are interested in what content will be presented to you so you spend more time in front of the screen. That is a little bit different than the machine learning approaches that we are proposing for accounting researchers. The machine learning approaches that we are proposing are just, you need to define the set of input variables and you need to define the output variables. Now, after you have defined these, the machine will find the best combination, linear and nonlinear, of these inputs to produce a decision rule.
But this approach is still based on the statistic.
Oh yeah, there is a lot of statistics embedded in it.
Okay. 100%.
There is statistics and there is math embedded in it. So let me go over the examples, and maybe after that we can retake these. But these are actually very nice questions that I wish I had, like, the paper's now like 70 something pages. But probably we can, but we certainly define very clearly where machine learning ends and where machine learning starts.
Okay.
Now, artificial intelligence is the sort of the frontier of machine learning. But honestly, I don't think accountants need to go to the frontier of artificial intelligence to improve a number of decision rules that we have modeled in accounting, right?
Hey, Miguel, sorry,
Yeah.
but like, don't you worry that the black box nature of some of this is just going to lead to a lot of really bad research? Because like you say that it, like you said that it finds the best relation, right?
Mhm.
But that's glossing over lots and lots and lots of stuff, right? Because like even a deep neural network is really just, it's optimizing over a ton of parameters in a way that you're telling the computer to optimize over it. It depends on the initial seed value. It depends on, it potentially depends on what you said as the training sample and the holdout sample. And then if you take the predict, and I'm sorry, I got to run it in 15 minutes. So apologies for jumping the line, but like,
no worries.
Even if you get a good prediction in the first stage and you use that in a second stage, granted, the state of the literature right now is to ignore the fact that the first stage is a random variable when you go and run the second stage. It's extremely rare to adjust standard errors. And even if you have a linear first stage, we sort of understand how to do that. If you have a nonlinear first stage, it gets more problematic. If you have a nonlinear first stage with specification search, which is fundamentally what all of this is, then I don't think, I mean, maybe there's a bootstrapping solution, but it's not, I haven't seen like a, here's the right way to do it necessarily, that's feasible in finite computational time in most scenarios. So it, and I'm a little bit guilty of this because, I've got a PhD student who's working on this, and it does seem like a good idea to start using these flexible models in first stages that then you're, to predict some of these things that are really important. And then you're going to use those predictions as like a measure of risk in a second stage model, like linear regression or probit or something where you can do normal hypothesis testing. But this notion that like, this is a black box that solves your problems. It's sort of like you could think back to when instrumental variables became popular and people just picked like every friggin' instrument, and the instruments were terrible. Like none of them really satisfied
matter anything.
Unless it was a Powerball draw for like, unless it was true randomization. So I guess the question is really like, how concerned, and feel free to defer this or say like, that's a good point, we're not going to talk about that.
No, we talk about that in the paper. We talk about that in the paper, and we want to add a word of caution to what you're saying, right? So people need to understand what can you do and what can you not do doing these. The first thing you cannot do is to think that your rule is how the world actually works, right? Because I can predict whether a company can have a Big Four auditor. The paper is posted on SSR, and somebody just sent me a chat. And the new version will be next week. The thing, I can predict whether you have a Big Four just using size. And I get a very good decision rule. But that, I cannot be cheated into thinking that this is why a company selected a Big Four auditor. Because that's not how you go, right? There is board processes, there is decisions, there is voting. So one thing that we cannot cheat ourselves into thinking is that we create causal explanations for things. Now, on the other side, what we get, and this is where perhaps your student is going, we get less measurement error than with traditional two-step regression-based models of conservatism, of discretionary accruals, of earning signals, or any of that stuff. So we get a variable that most, or an algorithm that most accurately predicts the outcome, right? So if for example, you want to look at how, there's a paper that I really like that is like, of that stream. He predicts whether an auditor will switch, and then looks at auditors that have a very high probability of being switched, but they don't. And it turns out that there are some quality problems there, right? So there is some sort of independence compromise or some sort of issues in those observations that are close to the breakup. But I understand, and this is a concern that I think we need to have all in mind. We cannot think that this creates a causal model, but it can improve in our understanding of certain causal and uncovering new relations. I think this is where I like this research. I like this research if you sort of, yeah, you estimate your black box model, it's fine. But then you give us insights, and we make that emphasis in the paper. You use this to let us know what new variables I didn't know about. And there is a bankruptcy paper in Rust by a guy named Jones, 2017, that finds that one of the big things that predicts bankruptcy is CEO ownership. And I had not seen any other papers before that showed us that, right? And that's where I think it'll be interesting. It will lead to buckets of the data where the relationships are different. But then our role as researchers is to understand why, right? So it fits into a descriptive purpose, but we have to be very careful when we jump that abyss between hypothesis testing and machine learning. But yeah, Henry's concern is super important, and it's super important for our paper, and it's super important for this line of research going forward. So it's not like I'm going to answer that later. It's very important to answer that from the beginning, and then we say that in the introduction. But in this revision, we're going to talk about that gap a little bit more, or at least in the conclusion. It's a concern that I myself have, right? I don't want to be the next person advocating the new discretionary accruals measure, right? That will wreck years of the literature. There are some questions here. Does these models work on panel data? Yes. I don't want to get anybody mislead. The models work on panel data, but you have to come up with a way to incorporate the panel nature in the prediction, right? So how's another way to say this? Think of most accounting research, even when we use panel, we think of this as cross-section. All auditing research, most of auditing research that I've ever seen in audit quality, in audit fees, treat data as just a very large panel with repeated observations, right? And of course, we have things like cluster fixed effects and other things to deal with the statistics. But in reality, we're just trying to predict which observations will have a 1 or a 0. And here we have to think about what's a 1? A 1 ever? A 1 next year? And that's where the panel and the machine learning models, the same way as regression, they need to be understood properly by the researcher. You can 100% use this in panel. Everybody in accounting has done machine learning in panel data. All the data that we have is panel. But then we have to be very careful about how do we, for example, choose the estimation sample, the logbook sample, or the cross-validation strategy, right? For example, one thing that is being done in fraud is you use 5 or 7 or 10 years to predict the following year, right? So you have to think about what is the process that you're going to use to train your model, and what is the new data that you're going to try to predict new observations. That's all. You just need to think about that, and you need to come up with a reasonable solution, right? Let me quickly go over some of the alternatives that we are. Alessandro, yes.
Can I ask a question about spatial regression model?
About which regression model?
Spatial regression model.
I know a lot about that. Go ahead.
Okay. Another thing about also for the regression, when it is necessary to normalize the data. For example, I don't know, I want to understand the elasticity of some coefficient about ZDP, no? Gross domestic product.
Yeah.
using, for example, as explanatory variable, employment rate, and I don't know, quality of government, that is a variable that is centered around zero mean. Instead, the gross domestic product is in million euro, and the employment rates are percentages of the population. So it is convenient to standardize with a min-max the GDP and the employment rate, instead the other one, so the other variable through a normalization.
Yeah.
Okay. And to catch, to read the elasticity of the coefficients, how can I do that?
Well, I'll tell you a few things first. First, let's deal with regression, right? If we're in the regression world, if you are looking at OLS, normalization is super important, right? Why is normalization important in OLS? Because we have numerous variables that are really messed up. That I have a paper on robust regression, and that's one solution to that problem. But normalization is typically more necessary in OLS models with continuous variables, right? Now, let's move from OLS to logistic. In logistic regression, normalization is not as necessary because the outcome is 1-0, and because of, when you impose the logit model, is not such a big deal, unless you have some values that are really extreme, right? So normalization is not such a big deal in logistic regression, but it may affect your coefficients. And this depends mostly on how your variable is related to other variables. Now, once you move to machine learning, some machine learning techniques are invariant to normalizations, and some are very sensitive. And most regression-based does not require normalization, while Supok vector machine and neural networks do, right? So, to be honest, for predicting discrete outcomes, 1-0 variables, normalization is not very central, but it may be required. And in particular, if you have random forest and gradient boosting, is not a big deal, because those techniques automatically filter the data to deal with non sort of standard surfaces. Okay, so this is important. Essentially, the message is normalization may be required and is part of the thinking process when you want to predict something, right? And in particular, normalization is way more important when you have a lot of skewness, when you have very extreme observations, and when you have very extreme observations that don't repeat themselves over time. Or when we don't understand what leads to that skewness. In the case of a lot of OLS models, in estimating all sorts of elasticities, people do that. For logistic and for tree models, not a big deal. For these two, it might be a big deal. So, as it is often the case, depends. I think it depends less if you use a random forest and gradient boosting. Now, the good thing is that random forest and gradient boosting can be used also for continuous variables, right? Without requiring normalization. So I think that's a very good advantage. And that's why, that's one of my suspicions why these two techniques tend to work very well in predicting infrequent outcomes like fraud, even when the predictor variables are not very good, right? Which leads me to talk a little bit about that. Let me talk about this idea of the classification trees. The classification trees goes into this very interesting mindset that if you want to classify things into 1 and 0, the first thing you want to look is how the things in the 1 look and how the things in the 0s look and what attributes make you decide whether you're in this bucket or in this bucket. And then you don't see a variable simply as a number, right? For example, a very good one is the risk of ending in the hospital if you are infected with COVID-19, right? First big deal is men and women have drastically different outcomes. So the first buckets will be created. Let's suppose we're trying to predict, again, what is the likelihood that you're going to end up in the hospital with complications from COVID? You separate men and women. Then next, you separate people that are by age buckets, 0 to 10, 10 to 20, 20 to 30, and so on. And then you start seeing how the risk is monotonically increasing in every one of these categories. Then the other big thing is whether you have been vaccinated or you have not been vaccinated. Huge another category, right? And then if we put together enough of these categories, we can create a decision rule that ends up being very accurate. Now, the concept is amazing. Now, the concept comes with weaknesses. What are the weaknesses? That if we keep exploring a data set with enough number of partitions and enough number of trees, we will learn perfectly, right? So we essentially will learn everyone's names. We will have a company fixed effects. We will learn everyone's names and whether you get COVID or not. And then we can predict perfectly whether you got COVID in sample, but because you are not there in the next sample, we cannot predict new people. So there has to be an element of randomization that goes into the creation of these trees. And the second thing, other thing that people have discovered is that the best way to do this is with a system of called ensemble of trees. So we have a bunch of decision rules that are combined to come up with an ultimate decision rule, right? Now, the random forest works in a way in which there is a bunch of small trees, and every tree means a decision rule, right? Whether you're male or female, whether your age, whether your vaccination status. And then every one of these trees is going to give a vote. And then we aggregate all of these votes, and the outcome that has the majority of votes is the most likely outcome, right? So this is super interesting. And what gives random forest their power is this concept called bagging, bootstrap aggregating. All it means is that in estimating every new tree, we only use part of the sample and part of the variables. So every one of these trees is only going to produce a decision rule based on a subset of the data and a subset of the variables in a way that we have uncorrelated trees. And when we add a bunch of uncorrelated trees together in a voting decision, then we get a very good decision. Now, this is very different to regression. What is the output of this? Just a probability of the outcome being 1. Can we observe all of these trees? Well, it's tough. It's tough to visualize all of these trees in the way we visualize coefficients, right? All of these trees are in the memory. Once the decision rule is being trained, there is an algorithm. And that algorithm is essentially a map of all of the trees that are going to be used to classify new observations. How many trees can there be? Hundreds, thousands, right? So what researchers in this area have developed is measures of influence, right? So a variable that appears in a lot of trees is a highly influential variable. And that's as far as we can go, but we cannot say that a variable is statistically significant. We cannot say that a variable has a statistically significant association with the outcome. We cannot say that. We just can say that a variable is highly important in predicting the outcome. Now, there is a data package to do that. In the paper, we explain how it works. We give the tuning commands. And a big problem is that it's not entirely, it's not entirely to the machine to find the decision rule. Humans give input. And the human input is essentially a variation into the number of iterations and the number of variables that we use in every tree that may be different in every problem. And this is where the creators of these techniques understand that every data set is different. So they give leeway into changing some of these parameters to be used. And I understand hyperparameters a lot like cars. All cars look the same in several aspects. All cars, when you get in, you can run. But different cars have different gears, right? And jumping from first, second, third, fourth, there are different choices, right? And different drivers will have different ways to deal with these. And that's why, for example, a standard car or a gear car will always be better for high performance races than just an automatic changes, right? So the algorithms give us certain leeway into finding these parameters. How are we going to find these parameters? Through cross-validation. And this is just something that a grid search will help. Then gradient boosting is an improvement or a sort of a different mindset over the random forest. So instead of having a bunch of voters where there is democracy, let's say all of these voters give a vote and then we aggregate their votes. Now we're going to say, well, the decision rule is very good for this group, but it can be improved for this group. And then within this group, it can be improved for this group. So in this case, there is a sequential aggregation of trees, right? So instead of aggregating all trees equally, what gradient boosting does is it does a gradient search of trees, right? So you start with some prediction, and then you aggregate a new tree times a weight, and you aggregate a new tree times a weight, in a way that the new trees try to identify patterns among observations that are misclassified, right? So gradient boosting is more a sequential search to pockets of the data to find a better prediction. And in my opinion, that's not in the paper, but in my opinion, it works very well. And it works very well in accounting applications. And it's been used for bankruptcy, for fraud, for restatements, and is fairly stable and fairly easy to use. I'll probably still run both a random forest and a gradient boosting, but the gradient boosting seems a very good technique for accounting researchers. There is when do you use boosting? Almost always. When can you use boosting? Every time except when you have a small data set and when you only have indicator variables, right? So you have to have some variation because you want to create rules based on finding kinks in the data, right? So you want to find variables that higher than X, lower than X will give you prediction, right? So for example, to our COVID example, we can add the weight of the patient, their blood pressure, and etc., right? So we want continuous variables, many variables, and a large data set, which is almost in accounting, it's straightforward, right? There is a bunch of tuning options also in boosting. They're not a big deal. There are both recommended parameters from the literature that we give in the paper, and there is also possible to search through a grid. So what is this grid search? Well, you get your prediction accuracy, and then you vary, for example, the learning rate. And then changing the learning rate will give you certain accuracy. And ideally, if you find some concavity, you're gonna select the tightest. And this goes to Henry's concern, right? Like if you're just playing with the data until you find the best possible solution, isn't that concerning somehow? Well, it is not if you're always careful to have certain part of the data that is untouched to test your predictions, right? Because the goal is what decision rule will be the most accurate to predict out of sample, right? I'm gonna just, there is some, and just to show, and I showed this at first, how easy it is to do this, it just requires this line, right? For example, in our illustration, we use the probability of SEC investigation. We use 22 predictors. And then these are the parameters that you have to give to the model, and it runs, right? Now, is data the only way to do this? No, by far. There are applications There is a 4Pay called TreeNet, and there is also Python applications. But in our investigation, this data package does pretty well in being sort of turnkey and easy to be used. And one of our reviewers say, well, you can also say that an advantage of Stata is that you can do all of the data pre-processing to create your data set. You can also do the machine learning, and you can also do traditional analysis, right? So it seems to be a pretty unified way to do this. Is this the only one? No. R is pretty good. I think what I will do is I will start here, and if my paper hinges on boosting, then probably I will try the R version of it, the ROS boost.
I had a quick question.
Yes.
So for the gradient boosting,
Correct.
Does the predictors need to be indicator variables?
No, they can
Okay.
be. It actually works better when you have a mix and when you have a lot of continuous variables. Right.
So for the random forest, right? The variables need to be indicator variables.
Both. You can use indicators and you can use continuous variables in both. Now, if your predictors are only indicators, you may not be able to find that nonlinearity that these models are searching. Right?
Okay, yeah, great.
So if you only have categories, think about that. If you only have categories, you cannot sort of fit a nonlinear term to these categories to find where the space is more likely to lead to ones than lead to zeros. You see?
Yeah. Yeah, thank you. I had another question. So when we are creating the indicator variable, which threshold do you usually prefer, like median split or quartiles?
Oh, you don't need to do anything. You give the machine the continuous variable, and the machine through the boosting algorithm finds the cutoff. That is the advantage, right? The advantage of these techniques is that you are very free to give the data pretty much as is. You can even deal with missing variables, right? A big thing in accounting that we always sweep under the rug, right? Missing variables are always eliminated. In accounting, if there is one observation with one missing variable, we delete the whole row. In this case, you can create an indicator variable for missing. So it gives a lot of flexibility to use the data as is. And that is the advantage. And also, a big thing, and this is difficult to even write, and we've struggled a little bit with that, and look for the next version, we're gonna have something about this. What is very difficult to write is the idea that for logit, you need to have some technique to reduce the number of variables. But for a lot of these techniques, you don't have to. You still have to give a variable space. You still have to say, these are my variables, but the number can be huge, right? So for example, in that RAS paper that uses this to predict bankruptcy, they have, I think, almost 100 variables to predict bankruptcy, even when bankruptcy is a very infrequent outcome, and even when the bankruptcy data set is not very wide, right? So it gives you a lot of sort of freedom to give a data and produce a decision rule. Okay.
Thank you.
Yeah, no problem. And then the problem with that is like, well, then what's inside the machine? How the algorithm looks like? Well, the only thing you can do is create these, but it's not the only thing. I find this very powerful. You can create a visualization or a graph of influence, right? The influence is which variables appear in a lot of the trees. So which variables are highly predictive? And this will be, for example, here variables 1, 2, 3, 4 appear in a lot of the trees, while other variables do not, right? And this is super interesting, right? Because ultimately, you cannot just do, people that express concerns like Henry, which I agree with, will say, well, then what? You're just estimating a black box and giving me a probability? You have to tell me more. You have to tell me which variables are predicting, right? And together with the boost packet, for example, you can get this influence. there is a long question here. One of our recent publications was on machine learning. Yeah, this is something that it's my own experience. Machine learning models producing very similar predictions, let's say, as logistic. Yeah, it'll be very often the case if we understand the process very well, right? So for example, I think we understand pretty well how auditors give going concern opinions. If a company is struggling, doesn't have cash, has losses, has negative returns, and is highly levered, I can predict going concern opinions pretty well. Do I need a machine learning model to predict going concern opinions? I don't think so, because this is a process that we understand very well. So where I think machine learning has a role is into cracking processes that we yet do not understand well. And that's where I feel that accounting journals are changing. Accounting journals are more open to these. First, because now more and more reviewers and editors are aware of these techniques. At least I am. I mean, I'm at 2 journals and I'm a reviewer of others. And then there's Jeremy, and then there is Henry, and there's other people that are more open to these. But I think the tool needs to be introduced. The tool comes with a cost. What is a cost? That a lot of people do not understand it. So using this tool with a high cost, let's say, has to come in areas where we have a higher benefit. And that's sort of the problems that we need to be looking at. Instead of just redoing the past with machine learning. And I feel that that has happened in the fraud literature, right? So we had the Dichow paper doing logistic, then we have the Cecchini paper doing SBM, then we had the Bao paper doing boosting, and then so on. In that case, maybe there is a chance for a few first movers, but the chance is into cracking processes where there is a lot of noise and where we do not understand the assignment mechanism very well. Then there is, I'm not gonna spend a lot of time in support vector machines for numerous reasons. First, this is the machine learning machine where the predictions are the closest to logistic. It's also highly influenced by the definition of variables, and it's also highly influenced by outliers and by missing variables. We have it here because it has been used, that Cecchini paper in management science is very widely cited. People know about these, and it uses a different decision rule, highly mathematical, to separate the space, right? To say, to classify observations, we essentially need to draw a line that creates the most separation between observations, which is it's an interesting concept. It's a very interesting mathematical concept. It comes with a lot of jargon. But I find that it only helps, at least I haven't found personally where you will find these better than logistics or tree models, but it seems to work well when you have a well-defined problem with a high degree of nonlinearity. So we have a bunch of cautions about these support vector machines, but then there's also how to do it. It's also quite simple. And I want to move to neural networks because probably we're going to hear a lot more about these in the future. Neural networks used to be the beginning of machine learning a long time ago. Then it got discontinued because tree models were working much better. And because it requires a lot of mathematical notation, it requires a lot of computer power, and somehow it fell out of fashion. But now it's making a comeback in the form of deep learning, right? And this is really in the forefront of the connection between machine learning and artificial intelligence. A lot of the artificial intelligence machinery involves thinking like neural networks. So I think in the future, we're going to see more about these. And explaining them is tough, but then this image is actually helpful. So the idea is that we have inputs and then we make combinations of inputs that once weighted create a function of the outcome, right? And then here the advantage thing is that we can combine variable 1, variable 2 to create even simple. Think about a regression, right? So we have a regression with 2 variables that predicts another intermediate outcome. And then we take 2 more regressions that predict another intermediate outcome, and then those predict our final outcome. So there is a lot of possibilities to create very complex structures here called layers and intermediate steps, right? And for example, one case where I see a lot of intermediate steps is in the case of bankruptcy, right? Does a company with a loss, is a loss an indicator of bankruptcy? Well, no, unless you have several years of losses. Is that a big deal? Well, no, unless you are losing actually cash, not just accounting losses. Okay, so then I need several years of losses, and I need to be running out of cash, and I need to be a company not in the mining sector, because in mining companies are all going concern until they find the mineral, right? So if you're in mining, that's not the case. And you see how a lot of these variables can be combined and recombined to generate a prediction. And also another interesting thing is that in applications, although there are few, in accounting that require classifying into multiple buckets, neural networks can be very well used. For example, finding which critical accounting policies a company will disclose. Finding which risks will be disclosed in the risk section, and so on. So I find that neural networks, they have a high upfront cost because they have a lot of notation, they have a lot of mathematical jargon, they're difficult to estimate, they're difficult to explain, but they are good for certain type of problems that the other models may not. The other models can be used either continuous or dichotomous, but very few cases you have other prediction models that can help you to do multiple categories. And neural networks can be suited for that, which I think in accounting is an important thing. There is caution about all of these models, but there can also be at least one basic implementation is also available in Stata. There are way more sophisticated versions, but Stata has one that is workable. Now, one final word, I want to give a couple of, when I go back to the issue of accuracy. The issue of accuracy is the capacity of your rule to predict new observations. That's it. Now, what is a new observation? That depends on you. It depends on you, and it depends on how do you divide and subdivide your initial sample. Now, if you do this subdivision randomly, it might not be as good as if you do this subdivision in chunks of years, right? Because the world between 2000 and 2005 is maybe more relevant to 2006 than the world between 1995 to 1998. And some people may think that is counterintuitive, that you can use any observation in your panel to predict 1998. And that's what we're essentially doing, right? That's what we're essentially doing in most accounting applications. Our panel includes all years to predict all years. What do we do to feel better about it? We include year fixed effects. But in reality, we're pooling all observations. And when we do this cross-validation, we're essentially doing that, right? We're predicting, we're putting aside data from all years randomly. Now, there is, although the winner of accuracy is this ROC curve. The ROC is the percentage of, it accumulates the percentage of type 1 and type 2 error across all of the probability cutoffs. But there are others that might be useful for certain situations. For example, the precision recall curve, which is good to, it might be incremental when you have two models that produce the same ROC, but then one model maybe predict better different types of the space. And then there's another thing called the normalized discount cumulative gain at position K, and that's some more of a niche estimator, a niche indicator. And then there is also the log box, and the log box is a very interesting concept. And we're going to do that in our next version of the paper. It is a piece of the sample that you never use for anything except for your final test, right? So think about, in our case, in our paper, we try to, I'm going to go here. We try to model the probability of getting investigated by the SEC. This is a data set that we obtained from Blackburn et al. Thank you very much. We really appreciate that they were willing to share with us this data, the papers in management science. And then we start with, well, let's see if the variables that predict AARs also predict SEC investigations. And then we're going to use all our models, logistic, machine learning, etc. And then we horse race them, right? Now, in the process of creating all of these models, we can do cross-validation. But obviously, because every one of these models uses a different cross-validation rules, they step on each other's toes with respect to the estimation and the training sample. Sorry, the training and the auto sample. So what we did in this particular case is that we kept a log box that will be the last 1 or 2 years. I think we're going to do the last 2 years. No, the last year, sorry. The last year of the panel will be reserved for a final check. And that year will be untouched in any of the estimation process. And then that keeps us honest. And that helps us to say, well, in any given future year, how good will any of these models be at? And just one final word that I find really interesting is the issue of economic significance versus prediction power. And this, I think, was touched by Devin at the beginning. Partly, he was talking about cases that are non-frauds, never discovered. They will never be mimicked by a machine learning. There is another problem. There is a different cost of misclassifying ones and misclassifying zeros. And this is the problem with fraud. And there is a great paper by Daniel Benage that deals with this. We cited in the paper, where misclassification of non-frauds is not a big deal, but misclassification of frauds is huge, right? That's where machine learning sort of cannot give an answer. That's where accountants need to step in and then look at the differences between economic significance and prediction power, and also create statements like these. Going concern opinions increase the predicted defaults by 4.4% without increasing type 2 errors, right? Where we need to say, well, there is a trade-off, and we know that the trade-off exists. Besides that, there is a lot of uses for the estimated probabilities. It's not just the matter of creating a decision rule. If you have a good decision rule, other people will use it. And that's the case of the Dichow et al. Score. Now it's called F score, right? Besides that, thank you very much. This topic is so big and it's so exciting, and there is a lot of things that can be done, right? Our paper sort of stopped short of giving an introduction, an overview, and the very basic tool for a lot of you guys to start using it.
I had a quick question on the economic significance.
First, thank you very much, dear Professor Miguel, for your contribution and your effort. Thank you very much. Really an excellent presentation.
Yeah.
Now,
if anybody, can I just step a little bit over that? If anybody wants to have some answers or some specific things, I'll be happy to discuss further or give you comments or point you to any direction that you may. I'm not going to make the slides available because they're preliminary work. What will be available is the paper. The paper will come out published hopefully soon, and the next version will be on SSR.
Thank you very much, dear Professor Miguel. Now, if anyone have any questions, you can open your mic and ask a question.
Hi,
Question,
I had a quick question.
First, sorry. Question from Noor Albissa. You can ask.
Yeah, we can.
Yes, please.
Yeah.
Yes, please, doctor. I have a question. As a beginner in this research area, I want to ask if I want to apply this methods like machine learning or deep learning for a new standard in accounting, like IFRS 9. How to get the correct data or set of data? Just use the first year for application, or a serious time for applications?
Well, there is no rules, except ideally you will have a lot of data. A lot of cases, for example, let's suppose risk. There is new risk on cyber, new discussion of cyber security risks. It's unlikely that you can do machine learning in the very first year, right? So you will need, let's suppose you're going to look at the causes and consequences of disclosing or not disclosing cyber risks. And you want a model of the probability of disclosing a cyber risk. Unfortunately, you need several years to train these, right? So I would probably not use these at the very, very beginning of something, but you need data sets in the order of thousands of observations, right? So that would be my general rule, but hey, anybody can try. Yeah.
Like what, Dr. Yani, if I want to study this area, okay, for example, IFRS 9, the new standard in Egypt, it's a new standard in Egypt. So I need to take the whole years after the application of this standard.
Very likely, right? But it
like
depends what
3
you.
or 4 or 5 years.
Depends,
not
yeah.
just the first year for application.
Very likely, right? You need a lot of data. So this is the only. But to be honest, we also need a lot of data for accounting, right?
Yeah.
A lot of accounting papers, like in the US traditional setting, have thousands of observations. So this is fed for a lot of applications. But once you apply it to your particular problem, you need to be careful. The only rule is, hopefully you have a lot of data, and hopefully you understand your outcomes and you're determined.
Yes. Yes. I have another question, please. You said, doctor, that we are not depend on the hypothesis in these techniques in machine learning.
Depend on what?
Hypothesis.
Hypothesis, yeah. The problem is,
yes.
The problem is that you cannot make. Yeah, the problem is that you cannot make statements about association. So let's suppose you are predicting going concern opinion. Sorry for going back to that, but I understand that setting very well. And you want to say that Big Four give more or less going concern opinions. No machine learning model will help you to determine that. All we'll tell you is whether Big Four are more likely to enter into the prediction of going concern opinions. But you cannot create a confidence interval around that, right? So a hypothesis is a very clear statement. Is after estimated statistical model, there is up to 99 or 95% a confidence interval that tells you that this is not done by chance, right? We cannot create that type of testing with a machine learning model. Now, you can use the probability for a lot of other things, but you cannot use the machine learning output or machinery to do a test of the association between dependent and independent variables.
So we can get the effects or the impacts between the variables outside. You can only know, you can only rank and use.
Sorry for talking over. You can only rank the importance of the predictors.
Yeah.
Yeah.
Okay. Thank you, doctor. Thank you.
All of these very relevant questions, actually. Thanks a lot.
Thank you, doctor. Thank you.
My question was on the actually the economic significance versus predictive power.
Yeah.
So in not in machine learning context, but in usual context. So if we have some variable significant, but it does not include it doesn't increase the pseudo R square maths. I mean, including the variable. Does that matter? I mean, or it doesn't matter at all, the new variable?
Very likely it does not matter for prediction. The problem of T statistic and R square is that in regression, variables depend on their conditional independence, right? Depends on how variables are related to each other, right? So sometimes you can have two variables that predict an outcome, but they are related between each other in a way that if you have, for example, size measured as total assets and size measured as market value, and size measured as sales, only the pockets that are not captured by each other in their correlations are going to flesh out in a traditional regression model, right? That's not a problem in machine learning, right? Machine learning, actually, you can put all of these indicators without them stepping on each other's toes. Now, the problem of significance in prediction is it only matters if it gives you a higher ROC, or in other words, a higher R square, right? It doesn't matter if he has T statistics. Actually, T statistic in models like if you look at my paper on going concern opinions and bankruptcy, we just show T statistics, but I could have run that paper only with ROCs. The only thing that matters is, does this signal increases my accuracy in predicting outcomes? Yeah. Although the T statistic, I think for accountants, it will matter a lot. And you will never find, I don't think, I actually don't know that, but I think you will never find an increase in ROC by a variable that is not statistically significant. But you can have the other way around. You have statistically significant variables that do not increase the ROC or the R square. Look at audit fee models, right? Yeah. People keep throwing stuff there, and it's always significant, but it's because of the size of the observation, the size of the data set. But a lot of people keep adding irrelevant variables to the audit fee model. So I will definitely, the winner criteria is model fit out of sample. And I think a lot of those cases, if you do an out of sample test, it will turn out that the variable does not increase the prediction accuracy.
Yep. Thank you for your presentation. It was really helpful.
No problem. I'm like you guys. I mean, I'm an account researcher that does accounting. That sort of, my question is, can we put in a single set, in a single document, can we put guidance for the average accounting researchers to get started and run with data? Or with, at the beginning, I was thinking of R, but it turns out that with data, which is available to most of us and understood by most of us, can I give people a toolbox to get started? And I think we achieved that, which I'm very happy. Hopefully we'll see this in print at some point. Paper has 80 pages, including appendices. So we have work to do, but I hope to see it, and I hope to help a lot of us. Okay.
Thank you very much, dear Professor Miguel, for your contribution and your effort. It's really, really an excellent presentation. Thank you very much. And all that remains for me to say is thank you everyone that joined us, and thank you very much for taking the time out to present to us today, dear Professor Miguel. It's been really appreciated. Thank you very much.
Thanks a lot. Bye.
And I hope to see you soon in Egypt, dear Prof. You are very, very welcome.
Dude, anytime. We'll talk. Bye.
Yeah, goodbye.